Hi guys, I am recording this since I won't be here tomorrow or for you today while I'm at a cross-country meet, but I wanted you to stay on track with the other class. So let me explain what's going on. You have some graphs in a set of notes. Your notes will replicate this smartboard, and you are trying to match these graphs with a story, even though right now you don't necessarily know very much about the story. So you're going to try to match number 1 with A or B or C, etc. A couple things I want to show you. Hopefully this is review for you, but notice that here we have this line that seems to mean that Tom is getting farther away from home. So one of the questions I would have for you is, what is Tom doing in picture E where he goes away from home and then his distance stays the same while time is going on? Well, hopefully you're thinking it means he's staying still. If the distance starts to decrease and he ends up back where he started, then that would tell you that he's changed directions. By the way, all these graphs are for something that's in one dimension. This picture does not mean that he climbs a mountain, goes across the top of the mountain, goes down the other side. That is not what this means. This is a mathematical representation of one-dimensional motion. I do want you to take special care to pay attention to the slopes. This slope is less steep than this slope, which would mean here he goes slower, here he goes faster. So if you would take 5 to 10 minutes depending and go through and try to match up every graph with your stories, and then in a little bit we'll go over the answers together. Okay, so hopefully you paired A with number 5. Tom left his home for a run. The steepness of the slope shows you how fast he's going. So this line gets less and less and less steep until there's a slope of 0, which is where he stopped. So A goes with number 5. For B, you should have made up your own story because this picture doesn't match any of the stories. You could say something like, Tom left his home at a constant velocity, realized he forgot his phone and started to walk back towards his house, then found his phone in his pocket and resumed his forward journey. He never quite makes it home because this line never gets back to 0. In this graph C, you should have matched with number 4. Notice that here he is going less fast. The slope is less steep compared to here. Of course, in the middle the slope is 0, which means he is at rest. In this graph, he is continually moving away from his starting point, and his velocity is increasing for each segment, which when you're running down the mountain, you're probably going the fastest. So D goes with number 2. E goes with number 6. F would go with number 3. Here, his slope is getting faster and faster and faster. Here, it's getting less steep as he slows down. Here, he speeds up again. G should go with number 1. H is problematic because at this point in time, he's here and here. So H goes with number 8. He cannot be at 2 places at the same time, which means I is going to go with number 7. Now none of the pictures match number 9. Maybe discuss with your table partner, how would you draw a graph of Tom walking slowly home from the party? So we're assuming that he's not at home and then he walks home. So think about how you would draw that picture. Okay, so you guys have notes, a packet to take notes on this. Normally I would be writing out notes, but you're going to have to really listen and write down what I'm saying. And I'll try to show you 2 different slides. So one of the first things we want to talk about today is the difference between displacement and distance. Okay, write this down. Displacement is a vector, which means it has both size and direction, and it's defined as a measurement from where you start to where you finish in a straight line. Sometimes you would call it as the crow flies. Distance, on the other hand, would be a measurement of the actual path traveled. It is a scalar. Now think to yourself, when would displacement and distance be the same value? Well, the only time they'd have the same measurement would be if you were moving in a straight line. Let's see if I have my notes open from yesterday. Aha, look at this, magic. There's your warm-up. Okay, so this is what I would ask that you have written. The difference between displacement and distance. Okay, see if I can toggle back and forth. Okay, this next slide is looking at the idea of average velocity. And there's a couple things I'd like for you to know. First of all is that average velocity is defined as a change in x over a change in time, or x final minus x initial over t final minus t initial. This is one-dimensional motion, so the x could also be written as d, as in displacement. And you've seen this equation before, probably when you were like a freshman, as v equals d over t, or velocity, average velocity equals displacement over time. Notice that there's a difference between instantaneous and average. Instantaneous is at a specific point in time, and that's what your speedometer would tell you in a car. And your average wouldn't necessarily match your speedometer unless you were in cruise control. Another definition I'd like for you to get off of this slide has to do with the word distance. So distance over time is known as speed. And notice these notes that I had my other classes right. In a straight line, speed is the magnitude of velocity, and this is the mathematical way of writing the magnitude of velocity. So if your velocity is 25 meters per second west, your speed would be 25 meters per second. You can ask the sub to pause at any point in time that you're trying to get things written down. Okay. So look at this graph. We just finished a warm-up with a bunch of graphs. Here we have a graph where someone is at 1 kilometer at 0.1 hours, 2 kilometers just before 0.2 hours, 3 kilometers at about halfway between, and then they go backwards. Now the slope of this line is a constant positive slope and a constant negative slope. And because of what we just said, remember that the velocity is a change in x over a change in t, or rise over run. So the slope on a position versus time graph represents the velocity. So if you have a constant slope, you could also say you have a constant velocity. Okay, so now look at this next graph. By the way, these pictures come from your textbook, Open Stacks. So this x versus t graph, this is the same graph of the same motion, I should say, but the axes are different. So here's our positive velocity up to this point in time, followed by instantaneously a negative velocity. So this is not really physically possible because you can't change directions instantaneously. You can't change your velocities instantaneously. But mathematically, this graph is the same motion as this graph. One more. Here we have a speed versus time graph. Why is it a straight line? Well, remember, speed is the magnitude of velocity. So if you have a positive 12 followed by a negative 12, even though that's different on a velocity graph, it's the same on a speed graph. So make sure you can, in your own words, tell me the difference between distance and displacement and speed and velocity. Okay. Our last new term, which is for most of you probably a review, is acceleration. Acceleration is known as a change in velocity with respect to time, or v final minus v initial divided by t final minus t initial, where t initial is usually taken to be 0. So we end up with A equals v final minus a v initial over time. Having said that, if you have a v versus t graph, that means the slope of the line is the acceleration. So here we have another position versus time graph. These are actually all in your textbook, so I'm going to go ahead and go through these. Actually, let's look at this one. Here we have a velocity that's increasing over time, which means this object is accelerating at a constant rate. Here we have a slope of 0, so 0 acceleration, which means this car is in cruise control, going at 8 meters per second over a span of time. Here, the car goes from 8 meters per second down to 0 meters per second, and so they are decelerating at a constant greater value than the person sped up. Okay. If there's anything that we do today that is very important, here it is. Motion equations for constant acceleration in one dimension. This is a very fancy word for kinematics. And kinematics means constant acceleration. All right, so here's the notes that I wrote in my other classes. When we're dealing with kinematics, we have 5 different variables. Those variables are v naught, which stands for initial velocity in meters per second. A v all by itself stands for final velocity in meters per second. A stands for acceleration, which is always measured in meters per second squared. D is displacement, which is always measured in meters. T is time, that's always measured in seconds. Now, we are looking at problems that specifically have a constant acceleration, and we need some equations. So the first equation is just based off our definition of acceleration. Well, average acceleration equals your instantaneous acceleration if it's constant. So if I rewrite this, notice I dropped the t naught because t naught is 0. I do a little algebra, I get my first kinematics equation, which is v equals v naught plus at. Okay? This is a little bit more complicated. Let's see if I can scroll down. Okay. So on a v versus t graph, if I have a line with a constant slope, that represents constant acceleration. Now you can see me over here, I was talking about the area under the curve. And the area under the curve in a really simplistic way, like if we only looked at the rectangle, would have been velocity times time. And doing dimensional analysis with our units, we'd get meters per second times seconds. Well, the seconds cancel and we get meters. Well, what do we measure in meters? Displacement. So on a v versus t graph, the area under the curve is the displacement. The slope of the line would be the acceleration. So here I wrote an expression for the black rectangle and the red triangle. This would probably be good to write down. And then I did some algebra. Collected like terms, did a little rearranging. So in the blue box I have my second kinematics equation, which is d equals 1/2 v naught plus v times t. Now listen, if we had time, we would substitute this equation over here and we would get the rest of our variables. Or sorry, the rest of our kinematics equations. But here they are. Go ahead and write these down. Don't worry, I didn't do all the algebra in the other classes either. This is kind of our note card. The blue equations here are for kinematics. Up here in black is our good old v equals d over t, which we can only use if the velocity is constant. And then if we have something in free fall, I just want you to make a note that acceleration is g, where g equals 9.8 meters per second squared. And the direction is usually down or towards the center of the Earth. Now we're ready to start solving kinematics equations. Good job!